Hi, my name is Jean-Sebastien Laperriere, and I'll be presenting the paper Packing, Stacking, and Tracking, an empirical study of online user adaptation. This work was done in collaboration with my colleague, Darryl, and under the supervision of Kotaro Funakoshi. We'll first start by a quick summary. In this paper, we apply online user adaptation in multimodal interaction. We compare expert tracking to other common approaches like stacking, voting, and packing. We test all of these in simulated noisy feedback settings. Both of our dataset focus on nonverbal features, with one consisting entirely of physical features. For those that are still with us, I'll present the relevant background information to better contextualize the paper's objectives and contribution. To interact with humans, a system must be equipped with machine learning-based modules that accurately recognize various social signals from different users. In a training dataset composed of interactions with many users, only a subset of the dataset might be similar enough to approximate the new user's behavior. Finding and using that subset of similar users in a non-line adaptation manner could substantially increase the accuracy of a module. To keep the module as domain agnostic as possible, avoiding verbal features and relying on physically diverse features would be preferable. All of this is of course easier said than done, which brings us to a research question. How can a module rapidly adapt its predictions to the behaviors of new users? To answer this question, we explore the use of expert tracking algorithms. Expert tracking is nothing new, and its process is relatively simple. It finds the most reliable predictors or experts at its disposal and then bases its predictions on the best experts. After each output, it receives a feedback which allows it to update the weights given to the experts. The weights represents the reliabilities. Expert tracking does not presuppose a stable statistical distribution behind the observation. With this in mind, the objectives of our paper were to empirically determine the feasibility of expert tracking for online user adaptation, to compare the performances with other common approaches, and to determine the factors impacting expert tracking's effectiveness. Before we delve deeper into the technical stuff, I'll present the contributions of our paper. It is, to our knowledge, the first effort to apply expert tracking to online user adaptation in multimodal human-machine interactions. We provide an empirical analysis of an expert tracking algorithm under different feedback settings, a detailed comparison of the performances of expert tracking and other approaches. Finally, we identify the best practices and the future directions. Now that you know where we're heading, let me present to you the general process of expert tracking, as well as the other online approach we chose to compare it to, stacking. To apply expert tracking to online user adaptation, a dataset built from interactions with different users has to be slightly adjusted. The data will be split by user or by groups of similar users. Each of these subsets will be used to train a model, which will be called an expert. During the interactions with users, the expert tracking will start to rely on the most accurate of these experts. This slight change adds two main difficulties. First, since we now split the dataset, we still need to make sure that each of the experts has enough data to be trained with. If a user-wise split is not possible, a group-wise split should be considered. However, it also brings up a new question. What is the similarity between users? How can two users be considered similar? On the right, you can see that the users have been grouped randomly to emphasize the fact that similarities should not be limited to simple physical attributes, as behavior would be heavily influenced by context and personality. Online user adaptation on its own brings a significant challenge. During the interaction, the user can randomly change behavior. This will directly affect the reliability of the experts. Therefore, the adaptation process never ends, and so the expert tracker cannot be locked in a state. Since we focus on physical features, this change in behavior could be a simple change in posture, which changes the range of movements done by the users. Could also be because a user has entered the conversation, so now the utterances will be split between the robot and the user. It could also be caused by a simple annoyance. As we've all done with virtual assistant, if it does not understand or question, we switch to a more robotic manner of speech and usually lock our posture. Let's now look at the inner working of expert tracking. As input, it receives a set of predictors, the expert, and each of these experts has a weight attached to it. Here, we start with even weights. At each trial, we receive the data instance, in our case from the dataset, in practice pre-processed from the user. The expert tracker then receives the expert's prediction and outputs a prediction of its own using the predictions and the weights. When it receives feedback, it can then compute the loss of each of the experts and adjust their weights accordingly. This is somewhat similar to the other online approach we use, stacking. Stacking is a statistical ensemble learning technique. In our case, it uses the same expert as expert tracking. At each trial, a blending model combines the expert's prediction to make a prediction of its own. We modify stacking for online user adaptation by retraining it after each trial. At each trial, we extend the training set by adding the expert's prediction and the provided feedback as new training data. We then retrain the blending model for the next trial. This requires balanced data. Therefore, to balance the classes, we apply simple data augmentation. We found that by simply adding the opposite data instance, the performances were improved. To empirically test these approaches, we use two datasets. The first dataset we use is the MPO corpus, where groups of 3 play a game 20 questions. Behind the scene, an operator controls the robot sensors. The groups were composed of friends, family members, or colleagues, and participants could leave and rejoin the game at any time. This corpus focuses on the Response Obligation Estimation Task, ROE. It is an extension of noise rejection and addressee identification. Each of the user's utterances is classified as ought to respond or ought not to respond. The corresponding dataset is composed of 14 dialogues like the one illustrated, where the 3 users form one virtual subject. The sound segments are extracted by automatic voice activity detection, and the labels are provided by one professional annotator. Here, the features consist of 49 nonverbal features. Our second corpus is the recently renamed Hazumi corpus, a corpus of human-computer dialogues in Japanese, where the user discusses various topics with a virtual agent controlled behind the scene by an operator. This dataset is designed for multimodal interest estimation, MIE. The task is then to determine whether or not the user is interested in the current topic. The MIE dataset consists of 39 dialogues where one subject is one person. The speech segments were manually annotated and their labels were provided by the voting of a few annotators. The features are 65 nonverbal features and 62 verbal features. Fermi component analysis was applied on the verbal features. I'll now present the experiments we ran using these datasets and the results we obtained. All of our experiments were done in a leave one subject out manner. This allows us to simulate a completely new user. Between each round, the expert tracking algorithm and stacking were reinitialized. This means we assumed the system could detect when the users were switched. This could be achieved by face recognition. After each trial, we simulated feedback by providing the label. To simulate an imperfect feedback module, we also added noise. Since the provided feedback is binary, this means we randomly flipped a proportion of the provided labels. To test our online approaches, we also added 2 baselines. The first is packing, where all of the available data, meaning everything except the currently tested subset, is used to train one single model. Also, voting, a simple majority voting among the experts. Interestingly, voting represents the initial state of expert tracking when the weights are evenly distributed. I'll quickly go over the implementation details. The experts were random forests from scikit-learn. Tracking, stacking, and voting use the exact same random forest to ensure comparable results. We chose an expert tracking algorithm developed by Bousquet and Warmoth, as it was one of the earliest algorithms to model the change of reliability of the experts. We implemented it ourselves using the default learning rate and the recommended mixing scheme. For stacking, we use an adapted version of a public implementation. Our experiments are split between two main settings. First is the full-length experiments, where all of the data of all the subset is simulated. This allows us to compare the general performances. Second is the initial adaptation, where we observe the adaptation of expert tracking. Therefore, we only simulate the first 10, 20, or 30 trials of each subject. For the full-length setting, the results can best be described as inconsistent. For ROE, all the algorithms perform better with the ought not to respond class. As for tracking, it was almost the best option behind stacking. It was also slightly less affected by noise. For the MIE dataset, however, the overall performance is poor. Tracking never exceeded voting its default state. This indicates a failure of adaptation. As for the baselines, voting performed surprisingly well on both datasets and significantly outperformed packing on the ROE dataset. For the initial adaptation setting, on the ROE dataset, we can see that expert tracking rapidly surpassed voting. However, on the MIE dataset, it stabilized in a state worse than voting, its default state. Overall, stacking is outperformed by expert tracking in short simulations. Stacking is also much more vulnerable to noise, as expected due to its small initial training set. On the basis of these observations, we discuss the implications. First of all, voting seems to work better than packing on subject-wise datasets, like the two used in this paper. Therefore, it is worth considering if the computational cost is affordable and if the dataset's format will allow it. The reason that voting works better than packing has not been identified yet. Our hypothesis, however, is that by mixing all the data from the different subjects, packing could suffer from overgeneralization due to the inconsistencies between the differently behaving subjects. In comparison, voting would have more reliable submodels that are individually trained with consistent data. This hypothesis implies that voting will not have an advantage over packing if the inconsistencies among the subjects are negligible. Unfortunately, expert tracking is not a silver bullet. While the cause of the inconsistencies remain unidentified, we return to the hypothesis of the divergent or inconsistencies among the subjects. In our experiments, tracking performed considerably better only with the ROE dataset, and voting was much better than packing in comparison to the MRE dataset result. This suggests that the divergence in subjects of ROE may be larger than in MIE. With regards to MIE, the textual features are rather dominant for the task. These features would be more consistent and less divergent than other nonverbal features between the subjects. This could be a reason that voting and packing show similar performances for MIE. Our results suggest that, especially for a noisy or divergent situation, separating the data by individual or group, to use expert tracking or voting, can be better than using a single bulk model like packing. A lesson we learned from this is that one must carefully choose the user adaptation approach based on the nature of the incoming data. If not enough information is available about the domain, voting would serve as a good default choice as it does not require feedback and gives acceptable performances. There are several opportunities to elaborate on this issue. First, the expert tracker could be jump-started by using better initial weight based on the visible similarities between the user, like gender and age. This rough approximation could jumpstart the algorithm in its search for the best expert and thus decrease the amount of mistake committed in the initial adaptation. Also, the expert tracker's weight could be used to fine-tune a bulk model. Concretely, these weights could be used to remove the worst expert rather than selecting a small number of best experts. This would possibly improve the performances while maintaining the generality of a bulk model. Expert tracking could be combined with transfer learning to better define a source and target by using the worst and best experts. Finally, other online learning approaches should be applied to online user adaptation, like online random forest and online transfer learning. This work was done in the Kyoto University Cooperative Intelligence Lab, funded by the Honda Research Institute of Japan. We gratefully thank Haruto Nishimoto and Kazunori Komatani for the multimodal interest estimation data. Finally, special thanks to the Canada-Japan Co-op program. If you have any questions, please leave them in the comments. We look forward to answering your question and reading your feedback. Thank you.